Welcome to the Sensorless Brushless DC Motor Control using a Majority Function web seminar. My name is Daniel Torres. I am an Applications Engineer for Digital Signal Controller Division at Microchip Technology. Here is the agenda for today's seminar. We will recall the principles of controlling a brushless DC motor. Secondly, we will discuss the back EMF sensing method used in this sensorless technique. We also cover the principles of digital filter and the so-called majority function. The last section of this seminar discusses the motor startup sequence and the sensorless operation. Brief description of the brushless DC motor control. In this section, we will discuss the principles of controlling a brushless DC motor, the 6-step commutation control technique, and its relationship with the back EMF zero crossing. A brushless DC motor has windings on the stator and alternate permanent magnets on the rotor. Brushless DC motors are electronically commutated based on the rotor's position with respect to the stator windings. This means to run brushless DC motor on electronic drive is required. The brushless motor is usually operated with one or more rotor position sensors since the electrical excitation must be synchronous to the rotor position. For reasons of cost, reliability, mechanical packaging, and especially if the rotor runs immersed in fluid, it is desired to run the motor without position sensors, which is commonly known as sensorless operation. It is possible to determine when to commutate a motor drive voltages by sensing the back EMF voltage on an undriven motor terminal during one of the driver phases. The obvious cost advantage of sensorless control is the elimination of Hall position sensors. A typical control circuit with three-phase winding connection is shown in figure. H1, H2, and H3, along with L1, L2, L3, make a three-phase voltage source inverter for connected across the power supply indicated by VDC plus and minus VDC. Stator windings A, B, and C are connected in start to the inverter. The method for energizing the motor windings in this sensorless motor control algorithm is the 6-step trapezoidal, or the 120 degrees commutation. The figure shows how the 6-step commutation works. Each step or sector is equivalent to 60 electrical degrees. 6 sectors make up 360 electrical degrees, or 1 electrical revolution. It is easier to discuss motor speed in these terms rather than electrical RPM, because when talking about electrical RPM, the number of motor poles need to be factored in. The relationship between mechanical and electrical RPM is shown in the equation. For every sector, 2 windings are energized and 1 winding is not energized. The fact that one of the windings is not energized during each sector is an important characteristic of the 6-step control that allows for the use of a sensorless control algorithm. When a brushless DC motor rotates, each winding generates a back EMF which opposes the main voltage supply to the windings according to the Lenz's law. The polarity of this back EMF is in the opposite direction of the energizing voltage. Back EMF is mainly dependent on 3 motor parameters: number of turns in the stator windings, rotor's angular velocity, and magnetic fields generated by rotor magnet. The back EMF waveform of the motor varies as both a function of the rotor's position and speed. Detection of position using the back EMF at 0 and very low speeds is therefore not possible. In this section, we will discuss the different methods used to sense the back EMF signals. The algorithm described in this web seminar is based on the midpoint voltage reconstruction, and it's also based on detecting the instance when the back EMF signal of an inactive phase is 0. Therefore, it is important to mention that the back EMF sensing method described in this application note can be only implemented using trapezoidal back EMF signals in order to have zero crossing events. This method is suitable for use on a wide range of motors. It can be used on both Y and delta connected three-phase motors in theory. Certain classes of connected motors may not work. It requires no detailed knowledge of motor properties. It is relatively insensitive to motor manufacturing tolerance variations. It will work for either voltage or current control. The zero crossing technique is suitable for a wide range of applications where closed-loop operation near to zero speed is not required. Back EMF voltage zero crossing signals can be detected by different methods. The most common sensing methods are comparing the back EMF's voltage to half the DC bus voltage, comparing the back EMF voltage to the motor neutral point. Both methods have advantages and as well as drawbacks, which will be discussed in the next slide. Both methods are based on the fact that most of the times the motor neutral point is not available, due to the fact that either it was not wired or the motor windings were built into a delta mode. This method consists of comparing the back EMF voltage to half the DC bus voltage by using comparators, assuming that the zero crossing events occur when the back EMF is equal to BDC divided by 2. Figure shows the circuitry used to implement this method. Let's assume that the motor is in the commutation step number 1, in which phase A is connected to plus B bus through the electronic switch Q1, and the phase C is connected to minus B bus through the electronic switch Q6, and phase B is open. The back EMF signal observed on phase B has a negative slope and its maximum value is almost equal to plus BDC, just before the commutation step 2 occurs. The phase B reaches the plus BDC value when the commutation step 2 occurs. At that moment, phase B is now connected to plus BDC through an electronic switch. Phase A is now open and phase C remains connected to minus BDC. The back EMF signal observed on phase A has a positive slope and its minimum value is almost equal to minus BDC, just before the commutation step 3 occurs. Both slopes observed on phase B and phase A are compared to BDC divided by 2 in order to determine the zero crossing event. This circuitry is easy to implement with 3 operational amplifiers configured as comparators. The drawbacks of these methods are: this method assumes that the motor windings parameters are identical. The sensed back EMF signals have positive and negative phase shifts. Motor rated voltage is less than the BDC voltage most of the time. Therefore, the zero crossing event not always occurs at BDC divided by 2. The zero crossing sensing method described before can be improved by having a variable threshold voltage point used to detect the zero crossing events. This variable voltage is, in fact, the motor neutral point. Often, the motor manufacturers do not wire the motor neutral point. However, it can be generated by using a resistor network. 3 networks are connected in parallel with the motor windings and connected together to generate a virtual neutral point. The method used in this